Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the new webinar series with academics of the ITU Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our fifth webinar of the season with Professor Chong Han from Shanghai Jiao Tong University, China. Please submit your questions via the Q&A channel. We will address them to our speaker during the Q&A session. After the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live life lessons. So please stay online. Professor An agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. So I'm very pleased to introduce Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and founder and president of Truva from the United States. Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. Professor Akildis has established many research centers worldwide, including in South Africa, Spain, Saudi Arabia, and Finland. He is editor-in-chief emeritus of impact factor journals and highly cited at the top of the most prestigious international rankings, visiting distinguished professor in several universities around the world. His current research interests are in 6G wireless systems, terahertz communication, metaverse, and communication in challenged environments. So Professor Akilditz, the floor is yours for your opening remarks to introduce our speaker and moderate the Q&A session. Thank you.
Thank you, Alessia. And I was adding something about the latest news about the journal. So dear distinguished guests, esteemed colleagues, and honored participants, good morning, good afternoon, and good evening, wherever you may be joining us from around the world. With warm greetings from Abu Dhabi, United Arab Emirates, it is my distinct pleasure to extend a heartfelt welcome to our global audience as we commence Season 4, Episode 5 of the ITU Journal on Future Evolving Technologies webinar series. We are privileged to carry this series forward with a distinguished lineup of visionary thought leaders who are redefining the frontiers of technical innovation. Today, it is a true pleasure to introduce one of the dynamic and young minds in our field, Professor Chong Han. And before we begin, allow me a brief reflection on the mission and impact of the ITU Journal. Launched in December 2020, the ITU Journal on Future and Evolving Technologies, in short form JFET, was born of an ambitious and transformative vision to bridge the divide between academia and industry, to accelerate the pace of global innovation, and to foster deep collaboration at the forefront of technological research. As a fully open access journal, ITU JFET is unwavering in its commitment to the democratization of knowledge. Our model guarantees that cutting-edge research is freely accessible without cost to either authors or readers. Each submission is subjected to a meticulous peer review process that upholds the highest standards of academic excellence with a clear emphasis on relevance, innovation, and real-world impact. The journal's rapid ascent as a premier publication is a testament to the dedication and brilliance of an exceptional team. I extend my sincerest gratitude to Sizo Ono-san, Bilal Jamusi, Alessia Mallarditi, Enrique Campilongo, Maria Otero, and the many others whose relentless efforts have been instrumental in shaping our journal into the globally respected platform it is today, the researchers, innovators, and thought leaders joining us. We warmly invite you to contribute your most compelling work to ITU Journal of FET. We also welcome proposals for special issues that explore the emerging frontiers of technology and help shape the next wave of discovery. Actually, I was adding this sentence to my speech. We just heard that our journal is included in the so-called DOAJ directory, which stands for Director of Open Access Journals, which shows that we are doing our job right. So we have, of course, other goals and objectives that we are hoping to realize in due time. Now, it is my great privilege to introduce today's webinar speaker, Professor Chung Han, a rising star in wireless communication with pioneering contributions to terahertz band communications. Professor Han earned his PhD from Georgia Institute of Technology in 2016. He currently serves as the John Wu and Jane Sun Endowed Associate Professor at Shanghai Jiatong University in China, where he also directs the Terahertz Wireless Communication Laboratory. He is the co-founder and vice chair of the IEEE ComSoC Special Interest Group on Terahertz Communications. His accolades include 2024 IEEE ComSoC RCC Early Achievement Award, the prestigious Bessel Research Award from the Alexander von Humboldt Foundation, and 2023 IEEE ComSoC Asia Pacific Outstanding Young Researcher Award, among others. He also contributes to the conferences and also as guest editors to leading publications such as IEEE Transaction Wireless Communications and IEEE JSAC, which stands for Journal of Select Areas in Communications. On a personal note, I had the pleasure of meeting Chung in my wireless sensor networks class at Georgia Tech around like 13 years ago, 2012. Even then, he demonstrated a rare blend of curiosity and initiative, approaching me to collaborate on challenging research on Internet of Things. Our early work resulted in several impactful papers, including one on cross-layer protocol modules for the Internet of Things. Chung later joined my broadband wireless networking lab at Georgia Tech as a PhD student, where he focused our efforts on the formidable challenges posed by terahertz band communication. Chief among them, the issue of limited transmission distance. Together, we explored a range of innovative solutions, including adaptive modulation schemes, constructive exploitation of multipath propagation, and the pioneering concept of ultramassive MIMO, which is heavily discussed for the 6G wireless systems. Ultramassive MIMO concept, originally developed in collaboration with another of my PhD students, Professor Joseph Journet, culminated in a 2015 patent and represented a major breakthrough in overcoming the distance barrier in terahertz communication. So Chung published, or is still publishing, many papers. Due to Google Scholar, his age index is 45 at such a young age, right? And the number of citations is around 10,000. Since then, Chung has continued to advance the frontiers of terahertz research at Shanghai Jiatong University, achieving remarkable breakthroughs that underscore his vision, dedication, and scientific excellence. Professor Han, or just Chung, we are honored to have you with us today. We look forward to an insightful, inspiring presentation. Ladies and gentlemen, please join me in welcoming Professor Chung Han.
Thank you very much, Professor Acutis, for the warm introduction. Actually, besides the bio, and I was really touched and many unforgettable memories came up into my mind. Thank you again, and also appreciation to Alessia, all the teams of the journal, ITU Journal, for inviting me here to sharing my understanding of the topic of terahertz communication. So I do look forward to it. Without hesitating, let me start sharing screen. And I hope my screens are seen by all of you. Okay.
Yes, all good.
Okay, thank you. My name is Chong Han. Thank you very much for attending the talk here. The title of my talk is Terahertz Near Field Beam Manipulation, New Quality Productivity. And let's see how it works as the title suggests. So first of all, regarding the terahertz band communication, right? Most of us know that it's some pillar technology for the future wireless communications, especially when we look at the KPIs required for the future communication, right? Either you look at the peak data rate, the user data rate, or many people now cares more about the integrated sensing and communication. So you care about the sensing accuracy, right? It simply means the quest for connection of everything anywhere all time is coming. And why do we need terahertz band, right? We talked about the KPIs from what we have for 5G and what required in the future. For example, 100 or even 1 terabit per second required data rate, or millimeter level sensing accuracy in terms of the distance. No need to say the angular or the speed accuracy, right? So why terahertz? By the way, we define the terahertz band between 0.1 up to 10 terahertz as a broad or general definition from the frequency perspective. I do understand, I'm aware that some people also refer to 0.3 or up to 3 terahertz. We think that's also fine, but we try to be more general and stands from the frequency perspective, right? From the 0.1 up until 10 terahertz. So the key benefit of the terahertz band, if anyone asks me, it will be the ultra broad bandwidth. And if I can add another word, it will be contiguous, right? So that's something you cannot expect from the lower frequencies for sure. But then people may say, hey, what about the free space optics, right? Sure, there are even more bandwidth in the free space optics. However, we all understand that's not something very new, right? It was raised many years ago, and the FSO itself faces many challenges that terahertz might not face, or at least at a less severe level. So what does the ultra broad bandwidth bring us? Two things: ultra precise in sensing as well as imaging, right? That's what we call one stone for two birds. The stone will be the bandwidth. The two birds will be both communication as well as the sensing. So that's why we regard terahertz is one of the key technologies for future wireless communications. Indeed, back in 2013 or 14, Professor Kudis led the group to publish one of the pioneering and one of the most influential papers in the community on terahertz communication. Then, after almost 10 years, right, in 2022, he led the team to revisit the old problem, of course, with the quotation mark, the old problem of terahertz, and we try to summarize everything that has been done, and more importantly, the new problems, the remaining challenges, the future directions that need to be done in the next decade, of course, centered around terahertz band communication. That was an invited paper by Transaction on Communications. If you have interest, please feel free to check it. So normally after the motivation or the introduction of the first slide, I would like to share with many fancy slides, photos, or even videos on the applications, right? There are many. For example, the metaverse, the space communication, e-health, digital twin, all the fancy or the buzzwords you have in mind that requires ultra high speed communication, and especially not seen for in daily lives. Sure, I can share many nice photos or even videos on that. However, here I would like to share something is happening or already happened. So that was done a couple of years ago. That joint efforts between UESDC and our Shanghai Jiaotong University, we established the Terahertz communication link in the FACU, which is the Olympics for the world university students. You can regard like that. What did we achieve? We transmit uncompressed 8K ultra high definition video in almost real time, and we achieved 84 gigabit per second as the transmission rate over the distance of 1.2 kilometer. So that's a great balance or the achievement of the both data rates as well as the distance, right? Because some people might say, oh, data rate is great in terahertz, but you cannot transmit over 1 meter or 10 meters. That's certainly not correct, right? Also, that's a milestone that we regard of terahertz application from the laboratory to the practice. So that's something we have done. And of course, you probably want to check more applications that has been recently published or released in news. For example, in the US from our friends, Northeastern University Professor Joseph Jonette, they did it with other groups, also similar like long-range wireless communication in the terahertz band, or even integrated sensing and communication. You find those real examples, not the fancy photos itself. So that's the lesson. Okay, so coming back to the topic I want to share, right? There are many exciting topics related to terahertz, but here we, especially in recent years, we realized that a new paradigm of cross, far, and near field communications is emerging, especially in terahertz, especially with ultra large or extremely large antenna array systems. So why is that, right? If you look at the figure here, if you look at the transmission distance versus the so-called the relay distance, which distinguishes from near field versus the far field, right? Let's regard the default relay distance as it is. It's something proportional to the size of the array aperture. Also, it's inversely proportional to the wavelength, or like positively proportional to the frequency, right? That's why with higher frequency, with large antenna array, certainly we should expect a larger near field range. And especially in the terahertz, as we said, the near field range in this case could go to 10-meter level or even hundreds of meters. So in this case, users are in both far, that all the conventional communication systems serve, and near field region, which is normally ignored in the current wireless systems. And more importantly, they can switch between far and near. That's why we call it cross, far, and near field communication. We need to serve the users from both far and near, and also the cross in between. So that's something we regard as a new paradigm to address. If that's really new, if we check back the history or the electromagnetic history, right, we need to clarify some definitions. So first, after the signal coming out from the antenna, let's look at the photos from left to right, right? So first, it's called the reactive near field. It's something that your antenna operates in the near field, and the size or the length of that is on the order of wavelengths. So apparently that's something we do not need to worry too much. While if you look at the very right-hand side, that will be the radiative far field, like beyond the Rayleigh distance or the Fraunhofer diffraction equation would govern in this case. So in this case, all the papers you read about the MIMO system, beam forming strategies, beam estimation, beam training, almost 99% and over 99.9% of the papers are in this right-hand side far field radiation pattern. While what we called the near field, and to be precise, it's the radiative near field. It's something in between, right? So from the left mark, it's like on the order of wavelengths. On the right-hand side, the mark will be, for example, the Rayleigh distance, as we mentioned, could be extending to tens or hundreds of meters in the terahertz case. So this is the new case. This is the exciting case, especially of the topic of this talk. So that's why we call it a new quality productive force emerges, especially in this radiative near field. And we can do many things with that, especially with the beam engineering. I will talk more on this later. So if that's really new, let's recall, right? The terahertz band lies between the microwave and the optics. So especially this radiative near field concept was borrowed from the optics. And I am sure many researchers, especially the young researchers, are very good at and are fond of photography, right? So you play with your smartphone every day to take photos. So if you do not touch anything special, right, it's something like the far field beam forming on the left-hand side, as you can see. The focus will be towards that direction or on the far side, while your girlfriend or some female researchers will tell you, come on, focus on my face, the beautiful case. That's when you click on the face of the that's one of my PhD students. He was very brave to share the photos with me. So once you click on the face itself, right, it is something being focusing, and it is something to work with the radiative near field region. So it's not something totally new or invented. It's something we borrowed from the optical domain. And if you are interested, please check the paper from Professor Petrov, who is from KTH now, Daniel Middleman from Brown University, and Professor Joseph Jonet from Northeastern. They have a very good sharing on this idea as well. So let's continue. So we said that's a new paradigm, especially coming from the optics to the terahertz. At least we can envision three key challenges from left to the right, right? So first, the field boundary, no problem. We understand the Rayleigh distance has been there for many years, decades. Is that really correct or accurate for our use? Also, if we consider the near field, no problem. We have the spherical wave propagation instead of the planar wave approximation to it working in the far field, right? We can use it, but that's really efficient. And especially when we want to have the cross near and far field, is that still really true? So that's the first challenge regarding the boundary and well as the channel model. Second challenge is the beam forming and beam alignment, or the beams, right? So instead of focusing only along the direction, that's whatever the far field beam forming is interested in, only the direction. Now, with more room to play in the near field, we have the freedom from not only the direction, but also from the distance. That's why we have both angular and the distance to care when you work for beam forming or for beam alignment. So that's the second challenge we might need to be careful with. Third one, in addition to the Gaussian beam, whatever all the far field beamforming that follows, especially the amplitude follows the Gaussian distribution. That's the Gaussian beam we like. We always play that. Even I guess some of us might even forget the name of the Gaussian beam. Instead of working only with Gaussian beam, we can now have arbitrary beam shapes. We have more fancy playgrounds if we delve into the Bessel beam, focus beam, Airy beam, OAM, all the different things can come up. So that's the third challenge. We can be not limited to the Gaussian beam. We have the playground for the novel beam manipulation. So these are the three challenges we have in mind. And here's the overview of the main contents for today. So first thing, demarcation of the near field and the far field, right? So we understand that we have the relay distance, which is focused on the phase approximation, right? To be limited to pi/8. That's the error to be made if we approximate from the spherical wave propagation. It is working. It is, however, it is not very accurate, especially when we are communication people care not only on the phase, right? But more directly or importantly, we care about the channel rank or the spatial degree of freedom. Why? Because that's related to the key performance indicator, such as the channel capacity, as well as the channel diversity. So that's why we want to spend some time and efforts to work on the demarcation. So that's very theoretical, and I appreciate the collaboration with our colleagues, Professor Sun Shu and Professor Melissa Tao, to work on this interesting and indeed very theoretically challenging work. So I will not torture ourselves on the derivation of everything, but the key ideas is follows, right? So we try to derive everything, for example, for the different shapes of the antenna arrays, as well as the size of that. We focus the center of the spatial degree of freedom, or we call it effective degree of freedom. That's more related to the capacity that could be transmitted. So what's the lesson we have here after the derivation? We did the numerical evaluation and the relay distance, right? What we are very familiar, it may underestimate or overestimate the boundary. Basically, it's not that accurate. And especially for the URA to URA or the URA to URA cases, we derive the EDOF, effective degree of freedom based boundary that has certain relationship with the antenna array aperture. So that's something we did first as for the demarcation. Then we revisited the channel model, right? So first, the arrow of planar wave model, that comes from its derivation or the approximation with respect to the spherical wave approximation. So we know that the PWM, the planar wave model, is accurate only when the distance is much larger than the relay distance. So for example, with the 0.1 array aperture at 0.3 terahertz, that's only when distance much greater than 31 something meters. So basically, within that, all the indoor environment is not working. Then sure, we not only like the theory, we also like the experiment, right? We try to see it or observe it from our measurement. So what we did, we fixed the frequency to be 300 gigahertz, as we said. We can enlarge the antenna array size to enlarge the near field region or the boundary, right? So as you can see, we go from 16 by 16 to 32 by 32 up to 64 by 64. As you can see, now the near field region increases when it's even much larger than the communication distance. We should expect the near field communication or near field effect appears as is expected, right? So that's why you see especially the bottom three figures as for the phases, right? You see something linear, more or less linear. On the right-hand side, you do see certainly nonlinear phase changes over the vertical element index, which is for the antenna array. So that demonstrates the nonlinear phase change along the antenna elements in the near field. So that's something we like to see from the measurements. So now, what shall we do? We try to propose some channel model for the cross field, and we call it hybrid spherical and planar wave model. So that's a framework to say, sure, we have the very large antenna array. We divide it into several subarrays. Now, within the subarray, the aperture itself is not that large. That's why we can still invoke the planar wave model that remains precise to approximate the wave as a plane. The main purpose is to reduce the complexity. While the subarrays, among subarrays, the distance could be much larger than the wavelengths. That's why we need to have the spherical wave model to improve the modeling accuracy. As you can see, that's something hybrid in between for the lower complexity as well as improved accuracy. So the applicability or the accuracy of the HSPM, what we proposed, is accurate, especially it has very large applicable ranges, as you can see from the right-hand side figure, to evaluate, especially versus much better than the PWM. And under this framework, we do a bit more refinement to tell all the parameters involved in the channel model. For example, the path length, delay, the angle information. No need to say about the attenuation or the path gain, path loss, right? So we derived every channel parameters under the hybrid spherical and planar wave model framework to have it working, and we make it fully compatible with the 3GPP standardization like the favor. So that's what we derived for the cross-field channel model. So we want to say it is something working not only in the near field, but also in the far field with the good accuracy and the reduced complexity. You don't need to switch, right? That's why we call it cross-field. Next, the near field beamforming. So beam pattern based on the different scenes, right? So from the left, you see the planar wave only focuses on the direction, while the right-hand side spherical wave model, or based on the hybrid spherical planar wave model, they can focus not only along certain direction, but also they can focus at the user position, which means both angular and the distance domain provides degrees of freedom. So that's certainly good, and we try to have some scenario to analyze that. So the scenario we have in mind is the wireless backhaul. So in the good case, we have high gain antennas working in the terahertz with ultra broad bandwidth. However, the problem is with facing each other, the antenna arrays from both directions, from both base stations, right? Wireless backhaul, it has extreme sparse terahertz channel. Sometimes it's just line of sight, or at most plus line of sight, as well as the ground reflection. So we have many antennas to work with. However, we have the post-spatial multiplexing gain now limited by the sparsity of the channel itself. So the solution we propose, remember, we want to increase the near field region. How? We enlarge the spacing among the subarrays in the antenna system. So we propose the widely spaced, or sometimes people call it sparse antenna array, similar meaning, widely spaced multi-subarray beamforming architecture that increases or enlarges the range of the near fields. Why? Because with the spherical wave propagation kicking in, we have the degree of freedom not only from the path gain, it provides the additional spatial degree of freedom from the phase itself. And you can see the evaluation of the system now is point to point, as I said, like the wireless backhaul. it can be potentially improved to k times, while k refers to the number of subarrays. That makes sense, right? You have the degree of freedom of k. And if we extend it to the multi-user cases, now users, so for example, in the far-field beamforming, if all the users are in the same direction as shown here, we are more or less restricted. We can only serve along the same direction in the far field. Now, in the near field, we have the degree of freedom in the distance domain as well. That enables simultaneous transmission to users at similar directions. As you can see, the triangles are enlightened from the beamforming in the near field. So it provides 10 times or even more spatial degree of freedom, or that relates to the spectral efficiency for the sum rate, right? And for the beam alignment, so the good thing of additional degree of freedom is for beamforming, while it is something bad or at least challenging for beam alignment. Why? Because in the far field beam alignment, we only care about the direction or the theta. Now we need to care not only the theta, but also the distance. So the searching space becomes n squared times d squared. So it's a huge, right, computational complexity. So that's not something we want to do. And so the first question we ask ourselves is, can far field beam training, which you can find hundreds of papers in the literature, can they still be somehow used, deployed for the cross-field beam alignment in terahertz ultramassive MIMO communications? So that's the first and very natural question you need to ask yourself, right? So the answer is more or less yes, okay? Why? So sure, far field beam training can certainly be used for far field. That's makes sense, right? Very natural. While in the near field region, indeed, we expect the received signal strength to be reduced in certain ways. However, do not forget, we are in the near field, meaning the distance is limited. So, the reduction might affect, but might not largely affect the performance of the beam training in the near field. So that's the principle, right? That's why we try to have the far field beam training strategies with a little bit modified version to largely reused for the cross field. Now, of course, we can expect the great reduction of the complexity instead of or compared to inventing a total new near field beam training strategy. So that's the idea. And we admit, sure, there exists certain signal to noise ratio gap, but that doesn't affect too much about the beam alignment performance in overall. So that's the lesson. So far field beam training with estimation, certainly we also use the hierarchical strategy by dividing like into 4 beams with the subsequent layers. Then we have the two-phase beam estimator, especially we need to care not only the angle estimation, but also the distance estimation, which leverages the phase variation across the subcarriers to obtain the distance. So that mitigates the impact of the estimation errors. So the answer to that, yes, we can somehow largely reuse the far field beam training strategy in the cross-field case. That by doing that, we can have 30 times reduced training overhead while achieving near optimal beam alignment with like SNR only like 0.3 dB lower than the optimal one. So that's not too bad, right? And now the fourth topic is related to the near field beam engineering. So beam engineering, first beam propagation, remember I show you from the reactive near field to the radiative near field, now to then to the far field, radiative far field, right? They all can be prescribed by the electric field manipulation. And beam engineering essentially is to play with the electric field as a vector. Vector meaning we can control both the amplitude as well as the phase. Amplitude is possible, but that's a heavy burden for the power budget, right? While phase control is most people want to do, it's more effective and efficient. And that's illustration figures. You can see the manipulation in both amplitude as well as the phase. Of course, across the antenna arrays. So we want to show that we can convert the Gaussian beam, which is something emitted from the antenna, right, the normal antenna, to arbitrary beams. So that's the logo of our university, SJTU, as the example, right? We convert the Gaussian beam to the letters SJTU by designing its phase profile. And by showing this example, we are conveying the lesson, right? We can do almost everything, anything we want to play with that. And if we are allowed with the correct phase design strategy as well as the hardware support. So now I would like to share with you some examples of the beam engineering. The first one, we actually already covered that, the focus beam. That's another name that we use in the near field beamforming. Basically, that's the Gaussian beam in the near field region. So it's tightly concentrated EM wave with small spot size. And all the experimental results showing here are designed and developed in our Terahertz wireless communication lab. Now we use the Hexicon, as you can see, to enable that, to achieve that. I'm not saying that's the only or not even the best way to achieve that, but that's something we can do for the time being, and we are trying harder with that. So focus beam are especially useful when the applications requiring high precision, such as imaging as well as the sensing. So if you check from the literature, you see Professor Elder, Professor Lin Long Dai from Tsinghua University, they already studied heavily into those focusing beam for near-field multi-user communication cases. And essentially, they explore the degree of freedoms from both distance as well as the angle. And that enables efficient near-field multi-user communication, but also access with reduced inter-user interference, as you can see in the figures. What else? Bessel beam is a type of electromagnetic wave characterized by its non-diffractive nature and the self-healing property, allowing it to reconstruct after encountering obstacles. Okay, again, we show the measured E field versus the ideal E field from the simulation. So both experiment as well as the simulation. So this Bessel beam was very first introduced to the, especially the Terahertz community by Professor Joseph Jonet a couple of years ago. They tried to use it to circumvent or to overcome the blockage issue in the Terahertz communication, right? As you can see here, although the beam encounters the blockage as it travels, but because of its non-diffractive property and the self-healing property, after certain range, right, even after the blockage, you see the beam strength recovers, as you can see in the figure. And certainly, you need to play careful with the blockage, position, size, or even the shape, as well as the receiver position. And you need to have proper way to design and implement it. But theoretically and experimentally, or at least preliminary experimentally, they are achievable. So as you can see here, it can be used to address the blockage problem. Or sometimes you can think differently in the physical layer security perspective. You can try to avoid the eavesdropping, to resist from the eavesdropping by having the Bessel beam. That's another lesson you can think, right? If we can strengthen or enlarge the signal strength in certain near fields, it means we can reduce or mitigate or even zeroing the signal strength at certain region if needed. So that's the two sides of the SWOR, right? What else? Airy beam, that again describes a non-diffractive EM wave that can accelerate along a curved trajectory while maintaining its shape, allowing it to pass around obstacles, right? Again, that's the measured as well as the simulated ideal case. And we achieve it using the hexagons in the lab. So what is that useful? So that's something from our lab, and that's a collaboration with Huawei. The Airy beam that features the self-accelerating property that leads to a curved trajectory. So we try to think a good application scenario, and we try to use it in the terahertz wireless data center. Why? The propagation distance is somehow finite. It's restricted in the indoor data center, right? While we certainly require a very high data rate in the wireless data center, in many cases, we encounter the obstacles or the obstruction for line of sight blockage. However, the good thing is it's more or less static. So we can somehow design it to make the curves curved, right? Make the propagation of the beams to be curved. And that's what we recently studied heavily. We did the measurements. The results were published a couple of years ago, and more recently, hopefully soon you will see the results. We designed the Airy beam to be operated in the terahertz wireless data center. Okay, now we have not only the line of sight or the non-line of sight. Now we have the third case of, we call it quasi-line of sight, where we can apply the Airy beam to do the curving around that quasi-line of sight case. And certainly we show and prove that the spectral efficiency could be hugely improved in this case. For example, on the left bottom figure that we used with the Airy beam of the design. What else? Orbiter angular momentum, OAM. So that's a electromagnetic wave, also the radiative near field region wave. It's involved with helical phase structure carrying angular momentum, which means that can be allowing multiplexing or the information to be multiplexed in the modes, in the angular modes. That's how it can increase the data capacity in communication systems. Also, both the measured and the simulated results are showing here. Where shall we use it? That's a good question that we were thinking for a long time. So one thing we have in mind could be in the space where we can probably have the line of sight only, right? So now again, we have many antennas. We have lots of data to be transmitted. However, we only have the line of sight. Sure, we can use the beamforming to achieve certain gain. That's a good point. However, if it is possible to also explore the OAM modes to convey additional information in the helical phase mode to be transmitted. And that's something we did very recently and published in TAP, just appeared. So of course, we derived all the alignment issues, misalignment, closed form expression for the interference once we deploy the OAM in the inter-satellite communication scenarios. So that probably comes to the conclusion of the talk, especially for the content. So when we talk about terahertz with many antennas, that naturally forms near fields, or we call it cross-field communications. So I understand many people now are very interested in the near field region. However, be careful with the antenna array size as well as the frequency, right? You need to have proper values for both of them if you want to have a reasonable assumption of the near field region. And the key thing, I think, is to identify the killer applications of near field region. For example, if that's just centimeters or within 1 meter, nobody will care, right? We need to have sufficiently large near field region, and we need to make it to be reasonable in certain applications. And we want to achieve additional degree of freedom. We want to have much increased spectral efficiency. I think that's something enabling the near field to be a real thing. So second, while the near field itself is not new, significant research efforts are still needed in like channel, as we said, demarcation of the field, right? Sensing, beam management, all the things we need to be revisiting the existing series or the network protocols, right? Now we have the users both in near field as well as the far field. Network protocols should be rethought, right? And near field beamforming provides distance domain, the spatial degree of freedom, but that comes at the cost of the beam training, right? Wave engineering in the near field opens up a new door of research as well as applications. So communication designs must account for both channel features as well as the hardware constraints, especially for the terahertz communication, like the higher frequencies. We need to be aware of both of them. So finally, I would like to share a little bit. I understand that's the talk not only on the research topics, but also on the research philosophy, right? So I might endeavor to share a piece of philosophy of research that motivates it myself. So that's something I learned when I attended the Humboldt annual event last year in Germany. So that's the sentence from Professor Sidney Brunner, who won the Nobel Prize 2002. It's not from communications. He was a chemist or the biologist, but I guess the ideas could be borrowed. So what he said, progress in science depends on new techniques, new discoveries, and new ideas. More importantly, probably in that order, okay? So looking back of our research, right, whatever I got trained from Professor Cudi's lab, and now I am working with my group of people, we think we are somehow following that, right? Measurement, system, and techniques, right? We are channel people. When we come into terahertz, we always think or measure or observe the terahertz channel phenomena. Then we try to observe and discover the propagation properties, right? As you can see in my today's talk, right? We started from the observation of the nonlinear phase effect that in the near field. Then we try to develop probably not only the channel models, but also many other theoretical models in communication. Finally, we are working on communication and the networking design ideas. So that's the order, right? From techniques, discoveries to ideas. So with that, I will conclude my talk and extend my appreciation to the lab members from Terahertz Wireless Communications Lab. Also, I, of course, thank again Professor Cudis and Alessia and ITU Journal's invitation. So that's it for now.
Thank you, Chang. Very nice presentation. I'm sure the audience appreciate that and also learned a great deal. So I'm hoping to get some questions, but I can start to open up the question Q&A session. In fact, I was planning to ask you questions about Bessel beams and Airy beams and also the orbital angular momentum beams, and then you covered all of them. So that was really interesting. So, but for the OAM, you mentioned that you want to use them for the near field in the intersatellite links. But when you look at the intersatellite links, the distances are enormous, right? I
Yes.
mean, so where does the near field comes in the intersatellite links? So can you elaborate on that, please?
Yes. Thank you, Professor, for the question. Indeed, we understand that the distance, especially in the space communication, it will be huge, right? At the order of tens, hundreds of kilometers. So it's very hard to have the near field region coming up when the antenna array are co-located. That's what we call it when the antenna arrays are in the one unit, satellite unit. However, if we have many units of the satellites to form the distributed systems, distributed antenna system, in that case, the near field region could be enlarged. And that's something we probably have in mind to have the playground or the possibility to leverage, for example, the OAM or maybe others of the near field communication. So distributed satellite systems.
Will that be practical? So that's my question, actually.
It is something very
is there?
brave.
So the question is near field possible in intersatellite links? That's the question, right?
Yes, yes. So according to our evaluation, so that depends on the frequency as well as the distance in terms of the antenna array, right? When we place the antenna arrays in the distributed manner, meaning among different and satellite systems, so that distance could be also large, which will contribute to the enlargement of the near field region. So that's the answer.
Okay, so here's another question that when I was listening to you. So just to repeat, the controlling beam shapes and propagation path are crucial, as you know, especially the ones that you talked about, Airy and OAM beams offer like new ways of increasing data rates, and also you can improve resilience. But did I miss that? Did you talk about the control of energy distribution in near field communication? Did I miss that, or did you not cover that? What is your opinion about that?
Okay. Thank you, Professor, for the question. Let me quickly go to the field. Okay. So to enable the manipulation of the beam, right? Basically, we play with the amplitude as well as the phase control. So as Professor Acutis just mentioned, right? If we focus on the amplitude control, yes, we can do many different or very interesting things. However, that relates to the power budget or the energy issue that Professor Acutis mentioned. So that's possible, but at a heavy burden for the power budget. On the other hand, a more effective practical way is to play with the phase control. We can consider it as the beamforming strategy to play with the phase shifters. That's the phase control, right? So it's a more effective and efficient way to enable the beam engineering through controlling the phase. So that's the idea of enable the beam manipulation. While Professor Acutis also you mentioned about the energy consumption or the energy control in terms of the near field communication and probably in the networking issue. We didn't spend much time yet into that topic, but I'm sure that's something very important because especially like beyond 5G systems, energy efficiency is a key concern. I can say that, right? So that's something I guess very interesting and new of the field. I didn't talk too much about it in my today's talk.
Yeah, and also you covered really everything about all these Gaussian beams and Bessel and Airy and OAM cases. Did I miss that? Did you compare these 4 different paths and show that which one enhanced the signal robustness or spatial resolution, and provide some suggestion which of these near field beam engineering techniques should be used? So you show them separately, but somehow, yeah, but you just showed Bessel, right? Did you do the other comparisons also?
Thank
Bessel
you for the
versus
question.
Gaussian, yeah.
Yes, yes. So to start with, we think the benchmark could be the Gaussian beam, so which is the by default, right? The far
Right,
field as well as the near field beam focusing.
right.
So we try to compare the performance, for example, in here, like Bessel beam versus Gaussian beam, or the later we also compare the Airy beam versus the Gaussian beam, which is the benchmark. But Professor, you are right. We didn't compare all of them together. The reason is we start from the application. So, for example, in the obstacle case, we already think that Bessel could be a good option. Like, for example, here, after the blockage, it can self-heal the signal strength. That's why we didn't use like OAM or the others. Sure, we can also compare it with the Airy beam, since it can also like curve around or bend over the blockage. We, at least as far as I know, we can do it, but it still deserves additional efforts or research to compare all the different beams in different scenarios to see which one is better or worse. Yes.
So there will be more opportunities to write papers, right? So it's good
Exactly.
for
And
the
by the way,
promotion.
this topic is quite interesting and new. So still not many people are in the field or understand deeply in the field. So I'm sure there will be more interesting ideas or the efforts from not only us, but also many other researchers.
Yeah, but I remember I served on European community panels. There were a bunch of proposals like almost 6, 7 years ago before COVID. They were talking about Bessel beams, and
Oh,
so there are some people that are working on it, but you're right, it needs more attention, and more people are coming into this subject. Actually, your papers are really good, kind of like leading papers that can help other community members to work on these subjects. So I have one more question. There are some questions, but I have problems to understand them. But anyhow, so now let's ask you another one. In the context of 6G applications, let us look like, my latest love, metaverse and extended reality. What unique advantages does near field terahertz manipulation offer that far field communication alone cannot provide? I hope the answer is clear, or it's too difficult.
Uh, your questions are always challenging, but I'm trying my
sorry.
best.
You remember my time, yeah.
It's okay. Yeah, much earlier I already got used to it. Which motivates us to think, right, deeply. I think that's the essence of the seminar or the webinar. So I think, for example, you mentioned about the metaverse. We can imagine that. So in the maybe finite dimension of a room, many users or user equipment to be connected with ultra high data rates required, right? So in this case, with the near field, whatever like beam strategy, right? It provides the additional spatial degree of freedom from the distance perspective. So not only the angular, but also the distance. So what are the key advantages? First, it can increase the signal strength by different distances and different angles. Second, it can increase the spectral efficiency or the data rates for the user equipments, again, from different or similar directions, different or similar angles. So this is not achievable by simply using the current far-field strategies. So that would be my answer if we think of the advantages of near-field communication for application like the metaverse. So signal strength improvement, data rate improvement, especially for the many users in the near field.
Yeah. Thank you. That's good. Good.
Thank you, Professor.
So there is also a question by Samuel Sani. So he thanks you, and he's from Sabancı University in Istanbul, Turkey. I think he's the student of Özgür Gürbüz. You have a project with her. So he says that many of these proposed techniques rely on MIMOs, like, also you focus on ultramassive MIMO. Then he says, what about the CISOs? Is why people are not focusing on the CISOs, but mostly about MIMOs and ultramassive MIMO? I know the answer, but you should answer it,
right? Yes. So I think if you look back about the history of communication, right, you see at least two trends very clear from the technology perspective. So first, the carrier frequency, it is increasing, right? It's not to the terahertz, we have to admit, but it's coming up, right, to the millimeter wave or demanding higher. Second is the number of antennas that is used. That's why we heard the name of SISO, MIMO, multiple antenna, then massive MIMO. Then I remember back in 2015 or 16, Professor Kudis gave the name of ultramassive MIMO, UM-MIMO. Now people also talk about extremely large antenna array with the race, the stuff, right? So that's something clear that we are expecting more antennas to be used. Of course, that brings the increase of the spectral efficiency, but also diversity, all the different advantages you can imagine with multiple antennas. So I think that's a clear trend to be observed.
Yeah. And there's a guy, Alfred Forley. He is all the way from Apex University of Liberia. So can you imagine, we are worldwide. Liberia, country in the Western Africa. So it's really interesting. So he had a bunch of questions, but I think I can try to take one of them. And can you explain how far field beams can still be effective in the near field domain despite misalignment?
Okay. So I remember I have slides on that. So for example, here we have 4 users, which are the red triangles. They are happily, okay, in the same direction, but not the same distances. So on the left-hand side, if we still stick to the far field strategy, beamforming strategy, we enlighten one beam towards only the direction, right? We cannot differentiate the distance. That's how the 4 users will receive the same amount of information. Certainly, maybe not good, right? On the right-hand side, when we have the near field, we have the degree of freedom from both angular and the distance domains. Now we can transmit or we can enlighten the 4 users individually. So that certainly helps increase the overall or the sum data rate. So that's my answer to explain it.
Thank you. And I just read some questions by the audience. They're asking about the recording of this webinar and all the other webinars, whether they will be available. All webinars the last 4 years are available on the social media, also in YouTube. It's free of charge. You can go and listen to all the presentations. And one guy asked also about the certificate. Unfortunately, we did not give any certificate for attendance, but I hope these webinars will help you to beef up your knowledge in these very hot topics in telecommunications. And I have one more question, and I will let Alessia take over because there's no other question. Thanks a lot again, Chunk. Everything's going really fine. And you can say I survived Achilles' lap, right? So here is another question. I cannot let you go. But this is an easy question, by the way. This is an information for the other participants. Are there any ongoing experiments? Actually, you have your own, and also Joseph has some, or prototype systems that have demonstrated practical performance gains from near-field terahertz beam manipulations?
Okay. So the answer is yes. From several groups, right? Professor Cutis mentioned, like my own group in Shanghai Jiaotong University, Professor Jonas' group in Northeastern University in the US. I also know Yasaman from Princeton University, Daniel Middleman from Brown University. Many of us have the experimental setups. So what are the experimental showing all the values, right? So for the improvement of the signal strength in the near field, we can expect clear, like I can't remember the exact numbers, probably like 2 times or like 20 times increase of the signal strength in the near field. Then for the data rate improvement, as I showed here, we can expect like 10 times performance increase in terms of the some data rates. They are all validated, not only from the simulation, but also from the experiment. And one more thing I would like to add is now to enable the near field beam manipulation, many of us are relying on the hexagon. Some people are trying to use the metaverse, the meta surface, meta surface. I am sure that's more challenging, but once it's built, especially for the terahertz frequencies, I think the gain or the benefits will be even more significant than the hexagon itself, for sure. So that's something ongoing. We are also collaborating with Southeast University in China. They are experts in meta surfaces. We talk to the electromagnetic people, the antenna people, array people. We are trying to move towards that direction.
Thank you, Chang. And also, I have to mention that there are some minor distortions in the communication because Chang is sitting in Shanghai. So unfortunately, we are in the, gigabit era, or, we are talking about terahertz band, and we still have these distortions. And I hope with due time, we'll fix all of these glitches in the communication. So Alessia, I would like to take over, and chunk is yours, and you can ask your questions. Thank you again.
Thank you so much, Ian, for moderating this session. Thank you, Professor Han, for your great talk. So now we move to the Wisdom Corner, live life lessons. So I will start with my first question. Looking back on your journey, what is the most valuable life lesson or even failure that you have encountered that shaped your path? And how can this lesson inspire or guide those attending this webinar?
Okay. So first of all, to be frank, right, we didn't prepare these questions or the answers.
Yeah.
So it's truly something in my mind right now.
Yeah.
So I would say, like Professor was joking, right? I survived with Professor Cutis. That's something really shaped or reshaped my life, or especially the career life. So not only we were trained by the research skills, but how we think of the problems, how we deal with people, or the research world is something we learned heavily from Professor Cutis And especially as the years go, the research skills remain, but those lessons become more important, at least in my experience. So I think if I can share only one lesson, like we all get failure. All the successful people you see, they got failure. Like, don't say I got rejected by paper, rejected by proposal. That happens. So if you look at the statistics, right, the successful rate is 10%, 20%, you'll be very great. And I still clearly remember Professor Acutis told me, look at myself in my stage, in my age, in my like fame, right? I still get rejected. I have good or better acceptance rates than many others, but still sometimes we need to be positive. And we are not fully trying all the time. We think back, we take the feedback and improve ourselves and be ready to try the next time. So it can be punched down by 100 times. You need to be ready and stand up the 101st time and fight back. So that would be my a piece of advice or the sharing in terms of that.
Thank you. Thanks a lot. And in your opinion, which areas of study in telecommunications field hold the most potential for future researchers? Is there any emerging trends or groundbreaking topics that excite you and that you would strongly recommend young researchers explore?
Okay. Thank you for the question. So there are many buzzwords, hot topics. If you check, right, many of them. Near field certainly is one of them. Not only in the terahertz. I'm sure I will be spending my career or most of my career in that field, but not only terahertz, right? Near fields could cover different frequencies, so that's a very good topic. You can many young researchers could consider. Then what else? Meta surfaces. That's something change the environment can be used for many things. I'm thinking terahertz for sure. Integrated sensing and communication, or even with the computation, right? Now everything should be centered around computation. So although we are communication people, we can think how to facilitate the computation. So very recently, I was talking to my group, how can we do the trial study of communication, sensing, as well as the computation. And that somehow evolves to the so-called embodied AI, right? You need to have the sensors to sense the world, the physical world. You use your smartness or your brain to think or your process or compute while you can discuss or talk to other machines. So that's essentially the embodied AI, right? So you can understand it from either way.
Yeah, very clear.
So that's pretty much I have in mind in terms of the trending technologies. I might not be very good at that.
Oh, no, yeah.
Then I would like to indirectly answer your question. I could share two suggestions. Okay.
Yeah,
So
please.
First one, look at the big guys, big famous researchers' papers, right? So we are in a free research world. So people share the ideas not only from the top, but also in papers. So for example, Professor Acutis, he's still writing papers. So if you want to check the latest ideas, that his papers will be the first stop I will do. And then of course you can name many others. And you think those are many fascinating ideas to do. Second thing, for the young researchers, I wouldn't highly recommend to say, oh, this is hot, let's do that. That is hot, let's do that. You need to have your own career and label, right? And I will say the basic research, especially the fundamentals, for example, math, electromagnetic theories. We love channel, right? You can see from my talk. All those things are the fundamentals of many different technologies. So the trending ideas or the buzzwords might change over the years. Those fundamentals will not.
Yeah.
Those fundamentals will be armed for yourself to be ready for whatever changes are coming in the new technologies. So those are the two pieces of suggestions I want to share with the young researchers.
Thank you. Very important.
Yeah.
Thanks a lot. And what first inspired your passion in your field? And how did you turn this interest into a meaningful career that you have? The first inspiration that you had to say, wow, this is a subject I would like to learn more about.
I think that again went back to the PhD training or the study into Professor Gildy's lab. So I guess, I mean, I travel a lot to conferences, to many groups. I think students started with some problem to solve. I think it's nothing bad, right? We try to solve a problem in a good way. That's very good. When I was very proud to show that to Professor Kudis, and also I remember I showed that to Joseph Jonet, they told me, yes, you did well, but more importantly, you are not only solving this problem, you are changing or you are helping the community. So think big, do small. I think that's something to create or to motivate my passion to change the community. Maybe that's a little bit too big, but at least we are trying to make the community better, right? I think that's also one of the goals of our ITU journal, right? For
Totally.
good. Yes. Then, sure, we have many ups and downs. There are many stories I can share, and we keep positive. I think good research will turn out to be good publication, will turn out to be good career, right? Maybe there are some steps in there. Do not only or do not simply look at the final destination, right? I want citations. I want many papers. You might, if you look at that too much, sometimes you do it differently. You do it not in the good way. For sure, we want to have more impact, high impact, but we want to have the good research that will lead to the good impact. I think the order matters, right?
Yeah.
Yeah.
Yeah, thank you so much for sharing this. My very last question is there,
Yes.
among your career achievements, is there one particular contribution, either professional or personal, that has had a profound impact on you or others? And what makes this accomplishment especially important, meaningful to you?
Okay. I probably only speak for myself, right? I want to
Yeah.
say, with my and of course the guidance from Professor Kudis, many others, also the joint efforts from the lab, the group people, we try to advance the terahertz wireless communication, like from the channel communication, sensing, many aspects of terahertz, to from theory to the real world applications. So I guess that's something we have been trying, and we will be continuing with that to advance the field of terahertz wireless communication. Yeah.
Very good. Thank you so much. Thank you very much,
Thank you,
Ian.
Alessia.
I'm very proud of you. The way you were answering the questions, you really matured. It's fantastic to see, especially as you mentioned that these questions were not given to you before. Alessia does it on purpose
Yeah.
because we want to have spontaneous answers.
Exactly.
So nothing was prepared, and of course, I thank you for recognizing my contributions to your career in the beginning. Of course, it was not easy, to remember that, Chong.
Yes.
But look where you are, and not only you, but also many, many others, right?
Yes.
So again, thank you, and I'm really proud of you. You did an excellent job, and the future belongs to you, my friend. So thank you. And before we leave, we have 3 weeks back-to-back webinars. So May will be full, but we have very interesting topics. Professor Özgür Akan from University of Cambridge will talk about Internet of Everything, from molecular to the universe. Very promising talk. On May the 6th, next Tuesday. And in 2 weeks, we'll have Michele Zorzi from Padua in Italy. He will talk about non-terrestrial networks for 6G and challenges and opportunities and integration of non-terrestrial and terrestrial networks. And then in 3 weeks, Emil Bjornsson, actually his name was there in Chang's presentation.
Yeah.
He's also very active. He will talk about so-called reconfigurable intelligent surfaces. He is in Sweden with KTH, as I remember. So on May the 20th. And then we have several more lined up. So we'll be busy until the end of June. So I hope you all will attend our webinars. Again, thank you. Have a nice evening. And look forward to seeing you again. Stay safe and healthy, folks. Ciao.
Thank you so much. Thank you so much, Ian.
Thank
Thank
you.
you, Professor Han.
Bye.
Bye-bye.
Ciao.
Bye-bye. Thanks.
Bye.